My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the electric motor. We'll be able to define the motor. We'll learn about the scientific idea of the motor, its mode of work, how to increase the power of rotation. So let's get started. First of all, what is a motor? The electric motor is a device that converts electrical energy into mechanical energy. Once again, it is a device that converts electrical energy into mechanical energy. And what about the idea of the device? Idea of the electric motor. The electric motor is based on the magnetic effect of the electric current. Or you can say it is based on the magnetic torque. Okay, this was about the idea of the device. And now, what about the structure of the DC motor? Okay, in front of you, you will be able to watch the structure of the motor in its simplest form. So we've got a coil that rotates, or the coil is rotated, okay, between the two poles of a magnet. Okay, and we've got two brushes, commutator and a battery. So once again, the device consists of a coil of fine insulated copper wire. Fine insulated copper wire wound on a laminated soft iron core or armature between the two poles of a magnet. And we've got two brushes. The function of the brushes is to allow current to enter and to leave the coil. Also, we've got something very important, which is the commutator or a split ring commutator. And the function of the commutator is to reverse the direction of the current each half cycle to allow the coil to move in one direction. So function of the commutator. What about the function of the commutator in the motor? It reverses the direction of the current. Each half cycle means twice a cycle to allow the coil to move in one direction. And of course, we've got a battery, okay? And don't never forget, it changes electrical energy into mechanical energy. Okay. Now, talking about mode of work of the motor. Okay, how does it work? When current flows in the direction AB, okay, when current is allowed to flow in the coil, side AB and side CD, okay, are acted upon by two forces. And if we want to determine the direction of the force, all you have to do is to apply Fleming's left-hand rule. Okay, and by applying Fleming's left-hand rule, it will be seen that side AB, okay, of the coil will be acted upon by an upward force, okay, and side D is acted upon by a downward force. These two forces form a couple. Okay, so we've got two forces equal in magnitude, opposite in direction, but parallel. Okay. These two forces, as I said, form a couple which causes the coil to rotate until it reaches the vertical position. Okay. When it reaches the vertical position, it is supposed to stop. But because of its inertia, it overshoots this position. Okay? As the coil rotates, the torque of the couple decreases until it becomes zero when the plane of the coil is perpendicular to the magnetic field in the vertical position. But as I said, the coil continues to move by its own inertia. When the coil just passes the vertical position, the two halves of the commutator switch over. The current, therefore, reverses in the coil, and consequently the directions of the forces on the sides of the coil are reversed. In this way, the coil will move in one direction. Okay, it is shown in front of you right now how the two halves switches over. And now talking about increasing the power of the motor, power of rotation of the motor. How to increase the power of rotation? So increasing the power of the motor, first of all, we have to use a set of coils. So by using a set of coils instead of the single armature coil. Okay. By the way, the coils are at equal angles to each other. Okay, so the coils are at equal angles together with a commutator which has a number of segments twice the number of coils. Okay. Also, the power can be increased by increasing the number of turns in the rotating coils. So by increasing the number of turns on each coil, and by winding them on a soft iron core or soft iron armature. What is the function of the armature? The armature becomes magnetized, so it increases the strength of the magnetic field inside the motor. The poles of the magnet also should be curved to produce radial magnetic flux. And this means that each coil has its face parallel to the field for much of its rotation. So the couple acting on the coil is almost constant and maximum, of course. And now talking about uniformity of rotation of the coil of the motor. Talking about uniformity of rotation. Actually, what happens when the coil is running, the sides of the coil of the motor, sides cut the magnetic flux lines, and an EMF is induced in it. So we've got induced current. This current will be responsible for uniformity of rotation. So during rotation of the coil, a current is induced in the coil, a current other than the current of the battery. So we've got two currents now, current of the battery and the current induced in the coil during rotation. Okay. The induced current causes uniformity of rotation of the coil of the motor as follows. When the coil tends to speed up, if it tends to speed up, okay, what happens to the induced current? Rate of cutting increases, the induced current increases, of course. So when the coil tends to speed up, the induced current increases. Of course, the induced current and induced EMF is proportional to the rate of rotation of the motor. And the operating current decreases, and this reduces the speed of the coil when it tends to speed up. Okay, simply because I operating equals I battery, which is constant, minus I induced. So when the coil tends to speed up, I induced increases because rate of cutting of flux lines increases. So I operating decreases. And what if the coil tends to slow down? When the coil tends to slow down, the induced current decreases. Okay, and when the induced current decreases because EMF is proportional to the rate of cutting. Okay, rate of rotation of the coil of the motor. So operating current increases when I induce decreases, and this increases the speed of the coil because I operating increases. So I operating increases when the coil tends to slow down, simply because I battery is constant and I induced decreases. Okay. Now we've got some questions. First of all, give reason for. The resistance of a conductor increases as its length increases. You know, we've got a direct proportion between resistance and length. Resistance is proportional to the length of the wire. Give reason. We want to know why. Okay. The resistance, electric resistance, of course, increases with the increase in the length of the wire because electrons collide with an increasing number of atoms. Okay? Because electrons, free electrons, collide with an increasing number of atoms. Also, a lone wire can be regarded as a group of resistances connected in series. So their resistances are added together. A group of short wires connected in series. So their resistances are added together. Another give reason, the electric resistance of a conductor increases as its thickness decreases. So we've got an inverse relation between resistance and cross-sectional area. The question is why? As the thickness of a wire decreases, there are fewer spaces. Between atoms in the cross-section through which electrons can travel. Okay. In addition, a thick wire can be regarded as a group of resistances connected in parallel. Can be regarded as a group of thin wires connected in parallel. So their equivalent resistance decreases. Another give reason, the resistivity of a material is regarded as a physical property. Resistivity of a material is regarded as a characteristic physical property, but the resistance cannot be regarded so. Why? Resistivity of a material, unlike resistance. What about resistivity? Is a constant at any given temperature. Of course, you know, resistivity depends in general on two factors. Depends on two factors, which are temperature and kind of material. So at a given temperature, yes, it changes when we change the material. So resistivity of a material, unlike the resistance, is a constant at any given temperature and is independent of the dimensions. We mean by dimensions length and cross-section area of a sample of that material. But resistance actually depends on length and area. You know, resistance depends on four factors: length, area, kind of material, and temperature. Okay, so resistance cannot be regarded as characteristic physical property. Another give reason, the electrical conductivity of a pure metal is high. Conductivity of a metal is high. It is so nice and easy question because there are many free electrons. Conductivity depends on the presence of free electrons. In metals, there are free electrons that are not bound. Free electrons means they are not bound to any particular atom within the material. Another give reason, in parallel electrical circuits, thicker wires are used at the ends of the battery than that used at the ends of each resistor. So we've got a circuit, okay, that contains a battery and group of resistors connected in parallel. But there is something we want you to explain. Yes, there are thicker wires at the ends of the battery. There are wires which are thicker than the ends of each resistor. Why? Okay. In parallel connection, the total resistance of the circuit decreases, of course. Okay. So the current, the main current, the current through the battery increases. And hence, thick wires are used or should be used at the terminals of the battery. But what happens to this main current? This current will split, okay, when entering a group of, yes, resistors connected in parallel. Okay, but this main current divides, splits when passing through the parallel combination. That's to say, the current through each resistance is much less than the current through the main circuit, and this explains why thicker wires should be used at the ends of the battery. Okay, of course thicker than the wires used at the ends of each resistor. The moving coil galvanometer cannot be used for measuring alternating currents. Okay, as a matter of fact, the frequency of the alternating current is much greater than the frequency at which the coil can oscillate because of its inertia. Okay, inertia of the coil. Consequently, the galvanometer just records the average value of the alternating current. And average value of the alternating current is 0. Another give reason, the moving coil galvanometer is provided with hair springs. It is provided with spiral springs or spiral coils. Once again, let me say it, give reason for. The moving coil galvanometer is provided with hair springs. Actually, it asks for the function of hair springs. Hair springs carry the current to and from the coil. Okay? They produce a mechanical couple. So, they form a mechanical couple which opposes the rotation of the coil, which counterbalances the electromagnetic couple. Okay? That's to say, it counterbalances the electromagnetic couple. Also, hair springs return the coil to its initial position, to 0 position, when the circuit is broken. Another give reason, the scale of the moving coil galvanometer is uniform. The scale is linear, scale of the galvanometer. It is equally spaced. Why? Because the poles of the permanent magnet are curved. Poles are curved to make the flux lines radial, to produce radial magnetic flux, radial to the core of the device, core of the galvanometer. In other words, the magnetic flux becomes uniform and it is parallel to the plane of the coil, perpendicular to the sides. Over the region in which the coil can swing. Consequently, the angle of deflection of the coil, angle of deflection theta, will be proportional to the current. Theta is proportional to the current, so the scale is uniform. Another give reason, the coil of the galvanometer is connected to a low resistance, we call it shunt, in parallel. What is the function of the shunt? It is to convert it into a DC ammeter, to convert the galvanometer into, yes, a DC ammeter. Function of the shunt, it extends the range of the device, and this means it enables the device to measure higher current intensities. It decreases the total resistance of the device, decreases the internal resistance, thus decreasing the heat produced in the device. Also, most of the current entering the device, yes, flows through the shunt, and only a small fraction of the current passes through the coil of the galvanometer, so it's not damaged or ruined. Another give reason, the coil of the galvanometer is connected, yes, to a high resistance in series. Connected in series to a high resistance. Okay, this happens when we convert it into a DC voltmeter. Why it is connected to a high resistance in series? We call this resistance multiplier. The function of the multiplier, first of all, it extends the range of the device. It increases the total resistance of the device. And in this way, because, yes, voltmeter is connected in parallel, when its resistance is increased, the amount of heat developed in it will be decreased. Yes, so it increases the total resistance of the device, thus decreasing the heat developed in the device during its operation. Another give reason, a current carrying wire is placed in a magnetic field, but it doesn't experience any force. No force acts on it. What is your explanation? Okay, the wire must be placed parallel to the field. Force is given by the expression BIL sine theta. Therefore, if the wire is placed parallel, the angle is equal to 0. Force is equal to 0 because theta equals 0. And sine 0 is 0. And this explains why the wire will not be acted upon by a magnetic force when it is placed parallel to the field. Give reason, a current carrying coil is placed in a uniform magnetic field, but no magnetic torque acts on it. No torque, no magnetic torque acts on a current carrying coil placed in a magnetic field. This happens in the vertical position. Torque is given by the expression BIAN cosine alpha. Okay. Alpha is the angle between plane of the coil and magnetic field. So the torque will be 0 when the angle between plane of coil and field is 90, because cosine 90 equals 0. That's to say when the plane of the coil is perpendicular to the field. This happens in the vertical position. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.